thank you very much. And also, thanks for getting up early. So what I want to talk today about is the heterotic F-theory duality from a math point of view, and in particular from the point of view of lattice-polarized state surfaces. And this is some ongoing project with Dave Morris. So the statement of heterotic F-theory duality is the following. It claims that the heterotic string compactified on elliptically fibered Calabi-Yau over a base is equivalent to F-theory compactified on a K3 fibered Calabi-Yau over the same base, where the latter also is elliptically fibered with a section. For the purpose of the talk, I want to focus on 8-dimensional compactification. So in the above statement, take the base to be just a point, the n is equal to 2, and then you see the data you have on the heterotic side. The Calabi-Yau is simply an elliptic curve with the principal G bundle, where G is the gauge group of the heterotic string. And for the purpose of the talk, I'll just focus on the first, even though everything can be done for the second as well. And on the F-theoretic side, your Calabi-Yau is an elliptically fibered K3 over P1 with a section. And for such an elliptically fibered K3 with a section, there's a description as a Weierstrass model. So what you do for each point in the base, you write down a Weierstrass equation to describe the elliptic fiber, where G2 and G3 are polynomials on the base of the appropriate degree. So now it is well known that the moduli spaces which describe both kinds of data are the same. It's the following Narayan space, which is the symmetric space SO2, 18 over SO2 cross SO18, modeled out by some arithmetic group, which I just wrote as SO2, 18 Z. Now, in a way, this is the basic version of the heterotic F-theory duality, the realization that the moduli spaces coincide. But what you can ask is, can you actually describe the map explicitly, which maps the heterotic moduli to the F-theoretic moduli, and in particular without taking limits? So usually this is done by going into what is called the stable degeneration limit or overflow limit. So let's get started and let's look at the F-theoretic side and see how the moduli describe such a Weierstrass model. This goes back to the work of Kodaira from almost 50 years ago. And what Kodaira tells you is that if you want to describe such a Weierstrass model, you have to know what the singular fibers are. So from these functions G2 and G3 in the Weierstrass normal form, you can compute the discriminant, and whenever this discriminant vanishes, it means that the fiber in your elliptic fibration is singular. And Kodaira classified all the singular fibers which can appear in elliptic fibrations over, let's say, P1. And you see the classification is done by the vanishing degree of G2, G3, and the discriminant. And then they have names. Here I only put a selection of all the possible singularities from the famous Kodaira table. And then what this table gives you is, in the last line, the monodromy action, the precise SL2Z action on the homology of the fiber as you loop around the singular fibers. And from the point of view of the Weierstrass model, you can also describe it as follows. So you started with your elliptically fibered K3 surface, and if you go to the Weierstrass model, what you do is to blow down certain subvarieties perpendicular to the given section. So the Weierstrass model, in general, has a total space which has singularities, and the singularities it has, depending on the singular fiber, are listed in the second to last column. And these actually have a clear interpretation in M-theory. If you look at M-theory compactification, these singularities generate the corresponding non-abelian gauge groups. So what Kodaira tells you, to define an elliptic vibration, what you need to know is the precise monodromy action on the fiber as you go around the singular fibers, together with an SL2C invariant function called the J function. And this classification theorem by Kodaira also allows us to map the math language of elliptic vibrations to the string perspective of scenarios of configuration of D brands in type 2D string. So this is what happens on the F-theory side, what happens on the heterotic side. On the heterotic side, so if you have a closed string on T2, there are two basic moduli. The complex structure parameter of your torus and your complexified Kähler modulus, which combines the B field and the volume of your torus. So again, you can think of this as being a parameter in the upper half plane. And now, if you look at geometric compactifications of the heterorodic string, which have a large volume level, what you usually do is you let tau, the complex structure parameter, vary over a base undergoing certain monodromies in SL2Z, but the complexified Kähler parameter is assumed to be constant, or at least constant up to shifts in the Z field. However, from a string perspective, both the complex structure parameter and the Kähler modulus should appear on equal footing. So what we should be really looking at are compactifications where both tau and rho are allowed to vary over the base, undergoing arbitrary SL2Z monodromies. In particular, rho might be mapped to -1 over rho. So at this point, you won't have a large volume limit anymore. So these ladder compactifications are inherently quantum, and to describe these was really one goal of our work. And then you see, as you approach from these quantum compactification in your moduli space, your boundary, where you have a large volume interpretation, you expect the complex structure parameter and the Kähler parameter, as well as some Wilson line parameters to appear. All right, so now what did we want to do? So our approach was the following. In this big and complicated modular space, which came from the symmetric space of SO2, 18, we are looking at natural subspaces, which are much simpler. You see, I've just replaced 18 by R, and what we are looking at are subspaces where this R is very small, where it's 2 or 3. And from a heterodic point of view, this will correspond to a situation where all Wilson lines are turned off, or where only one Wilson line is turned on in such a way that the gauge group E8 cross E8 is broken down to E8 cross E7. And the reason why we restrict to these particular subspaces is twofold. So first of all, there is something related to modular forms on these spaces. And in both cases, R equals 2 and R equals 3, the ring of modular forms, or Siegel modular forms, has been worked out in detail, so there's some machinery we can rely on. And the other reason is that we need a relatively high gauge group for a relatively high rank of our gauge group for our construction to work.
Sorry, does this restriction mean that you simply set some of the moduli to 0?
Yeah, but it's not, it's a little tricky how you set these moduli to 0, because if you go back here, you still want to allow tau and rho to, let's say, vary over the base and be allowed to undergo SLTC transformation.
Okay.
But you are right. In this picture, most of the moduli are set to 0, but our hope is that at least for the subspace, where a lot of moduli are set to 0, we can at least describe the full heterodic F-theory duality. Alright, so let's get started with the F-theory side. So what you first need to construct are the elliptically fibered K3 surfaces which correspond to these gauge groups. And this is not hard to do if you just look at the Kodaira table I showed you on the second slide. And here it is. I've written down a Weierstrass vibration. Y and X are the variables you saw before. U is the affine coordinate on the base. And these A, B, C, and D are parameters, moduli of the F-theory model. And if you set C equal to 0, you get the F-theory Calabi-Yau, which is related to the EA cross EA gauge group. If you allow C to be not 0, you get EA cross E7. So this had been done here, this had been done by Morrison and Buffer, this had been done by Abhinav Kumar from MIT. And from the perspective not of the Weierstrass model, but of the elliptically fibered K3 surface it describes, you can look at the Néron-Severi lattice. So this is the lattice, or the group generated by isomorphism classes of divisors modular linear equivalence, and if equipped with the intersection form, this becomes a lattice. And you see, there's a clear correspondence between the singular fibers and the lattice structure of this Néron-Severi lattice. And so this H is the standard rank 2 hyperbolic lattice, and it comes from the fact that our elliptic vibration has a section. So the class generated by the section and the fiber generates a lattice isometric to H. And you see the fact that we have two singularities of type 2 star leads to factors of the AD Néron-Severi lattice. So you see the rank of this Néron-Severi lattice is 18, and what this describes, this is the rank of this lattice is also called the Picard rank. It essentially describes how many parameters the devices on your K3 surface depend on. You can also look at the orthogonal complement in the K3 lattice. So K3 lattice has signature 319, so the complement will have signature to 2. It turns out to be H2. And the same structure can be worked out when C is not equal to 0. And what this is, it's sort of, it's a classical example of what is called a lattice polarized K3 surface. A K3 surface where you have a primitive lattice embedding of a certain lattice in the Néron-Severi lattice. So that's the F-theoretic side. Now, let's think about how the connection to the heterotic side comes in from a math point of view. And it comes in through an amazing Hodge theoretic correspondence between lattice polarized K3 surfaces and abelian surfaces. So let's start on this side. If you have an abelian surface, so it has the structure of the torus. On there you have the involution with 16 fixed points. You can look at the corresponding Kummer surface of this abelian surface by taking the minimal resolution of the double point singularities. And this construction is covered by a rational 2-to-1 map from your abelian surface to your Kummer surface, which induces a map on the transcendental lattices of the abelian surface to the Kummer surface. Now you say that the K3 surface carries the Shioda Innes structure if X is related in the same way A was related to the Kummer surface, to the Kummer surface of the abelian surface. And what that means is that these two, the K3 surface X and the abelian surface A, are tied together by a Hodge isometry on the transcendental lattice. Their two transcendental lattices are isometric. And this is how the correspondence between F theory and the heterotic string appears in this situation. So this is how you tie the K3 surface together with the abelian surface. And in fact, a theorem of Morrison proves that in the case we are looking at, there is such a Chiyoda-Inouye structure on our K3 surface, and you can actually construct it. Now, this is one part of the issue, relating the F theory to the heterotic picture. But now the other picture is how to get the relation to the modular space. And this comes from the fact that both for these polarized K3 surfaces and for these principally polarized abelian surfaces, you can construct nice moduli spaces using global Turanic maps. And I can't go into the details, but what you do as an analytic space, you identify the moduli space with what is called the period domain. And the period domain only depends on the transcendental lattice. But the transcendental lattice of these two, by the very construction, are isometric. So this is why their moduli spaces turn out to be the same. All right, now let's put all together. Everything we know is in this transparency. So what did we start out with? Let's start out with the case where all Wilson lines are turned off. You start with the lattice polarized K3 surface. You can compute its Néron-Severi lattice and its transcendental lattice. And then from the global Turani map, you can compute what the moduli are for such polarized K3 surfaces. And it's just essentially two copies of the fundamental domain for the modular group. Now we know that this K3 surface is tied together with the principally polarized abelian surface, but there are only two, the product of two elliptic curves and the Jacobian of the genus 2 curve. And you see here you have to match the transcendental lattice, so it's just the product of two elliptic curves, and you nicely see how these two modular parameters correspond to the two modular parameters of the elliptic curves. Now you can look at the period domain and figure out how these parameters tau and rho are related to the J invariants, which really describe the elliptic curves. So this is quite standard. And now what you do is you use the Chiyoda-Inouye structure to relate these moduli to the moduli on the F-theoretic side. And you see the moduli here are given by ratios of the modular forms, classical modular forms for the full modular group. And now you can also extend this picture to the case where one Wilson line is turned on. So now the modular space is a little bit more complicated. It's the Siegel upper half plane. So it's symmetric matrices with positive definite imaginary part. And just as modular forms describes the moduli defining this abelian surface, the moduli describing this abelian surface are given by Siegel modular forms. And in the same way as before, you can use the Chiyoda-Inouye structure to match the moduli here to the moduli on this side. And then that's the last remark. You get this very nice picture. As you turn off the Wilson line, your genus 2 curve degenerates into two elliptic curves, and these are exactly the elliptic curves you see here. That's it.
Question, right?
Yeah.
This duality 3 fibration, 4 fibration. It reminds me very much of the similar thing that can happen in T2 manifolds, where K3 in the torus is the typical example of cross-sectional submanifold. So I was just wondering if you know, is it connected to that?
Well, I mean, I think it's the same underlying idea. But the problem is always with these computations, what is doable? And the lucky coincidence here is that the modular forms for the full modular group and the modular forms for the Siegel upper half plane, the Siegel modular forms, have been worked out in detail. That, I mean, if you had to do all this work before, there's a long way to go, but in principle, you're right.
Is the story generalized to R greater than 2 or 3 in the same way, or you need to basically know a lot more structure to be able to attack the actual problem?
And it relates to his question. So we are actually working right now on the case R equals 4, which seems somewhat doable. However, I showed you this theorem of Morrison, which guarantees the existence of a Shioda-Inose structure for certain picarics. You don't have that anymore. This doesn't mean that this does not mean that the Shioda-Inose structure does not exist in these cases, but things are just getting harder and harder the bigger you make R.
Okay, let's finish the figure again.